Hello and welcome everybody to another episode of Books and Bytes. Today we're diving deep into the world of Michael Faraday, and his work on electricity is documented in his experimental researches in electricity. It's a 2-volume masterpiece. We've got a lot to unpack, so
Yeah, this is going to be a substantial deep dive. One of the most rewarding journeys I think you can take in the history of science, because Faraday's work is so foundational to our understanding of electricity. And these volumes give us such a window into his process of discovery.
what I think is so incredible is how much ground he covers in these 2 volumes. I mean, we're talking about volta-electric induction, magneto-electric induction, the identity of electricities, electrolysis, conduction, and insulation. He even tackles the idea of terrestrial magneto-electric induction, trying to connect the Earth's rotation to electrical currents.
It really is mind-boggling how he was able to connect so many different phenomena and lay the groundwork for technologies that wouldn't exist for decades, even centuries after his time.
So let's start at the very beginning. In his early experiments, Faraday was fascinated by this new phenomenon. He called it volta-electric induction. So imagine he used a simple setup, 2 coils of wire wrapped around an iron ring, to demonstrate how a current in one wire could induce a momentary current in another wire, even though they weren't physically connected.
It's a beautifully simple experiment, but the implications are profound. I mean, this is the essence of electromagnetic induction, the principle behind transformers and wireless charging, technologies we rely on every day. Faraday was essentially laying the groundwork for the electrical grid. That powers our modern world.
And what's so amazing is he didn't just observe the phenomenon. He meticulously dissected it. He discovered that the direction of the induced current depended on whether the current in the first coil was starting or stopping. Close the circuit and the induced current flows one way. Break the circuit and it flows the other.
It's like he was teasing out the secrets of this electromagnetic dance between these 2 coils.
I love that, the electromagnetic dance. And keep in mind,
And Faraday didn't have access to the sophisticated instruments we have today. He was relying on his sharp observation skills and this keen intuition for the behavior of electricity. He even managed to increase the strength of the induced current by using a more powerful battery, generating a tiny spark, a visible manifestation of this invisible force.
it's like he was pulling back the curtain on this hidden world, revealing the magic of electromagnetism. And he didn't stop there. From volta-electric induction, he moved on to explore what he termed magneto-electric induction.
This is where things get really interesting. Faraday discovered that moving a wire near a magnet, or vice versa, could also induce an electric current. Think about it. He's showing that mechanical motion can be converted into electrical energy, paving the way for the invention of electric generators, the workhorses of our modern power grids.
It's like he was unlocking the secrets of the universe, one experiment at a time. And he did it all with such precision and care, documenting every detail, every nuance, every challenge he encountered.
It speaks volumes about his dedication to scientific rigor. He wasn't just tinkering. He was systematically exploring the fundamental laws of nature.
And it's remarkable that he didn't just describe these phenomena. He grappled with their underlying nature. He introduced this intriguing concept of the electrotonic state to try and explain what was happening inside the wire during induction.
Yeah, the electrotonic state. It's a really interesting concept. Think of it as a kind of hidden energy, a potential waiting to be unleashed. He compared it to a state of tension in a stretched spring, ready to snap back into action. It foreshadows our modern understanding of electric fields, these invisible regions of influence that surround charged objects.
So he was essentially laying the groundwork for a whole new way of thinking about electricity, moving beyond just the simple flow of current to a more nuanced understanding of forces and fields.
And he didn't limit his thinking to the lab. He even hypothesized that the Earth's rotation and its magnetic field might induce electric currents in conductors. He tried to measure this effect in the Thames River, though his experiments were inconclusive.
Imagine that, the Earth itself as a giant electrical generator, even if he couldn't definitively prove it. It shows how his mind was constantly searching for these connections, seeking to unify seemingly disparate phenomena.
He wasn't afraid to push the boundaries of what was known, to explore those uncharted territories. And while not all of his experiments were successful, they all contributed to a deeper understanding of the nature of electricity.
Speaking of pushing boundaries,
Yeah.
one of Faraday's most important contributions was his work in establishing the identity of electricities. Back then, there was this debate about whether electricity from different sources like batteries, static machines, or even animals, was actually the same force.
He was determined to settle this debate once and for all. He meticulously compared the effects of electricity from various sources, using a galvanometer to measure their magnetic effects, and observing their ability to decompose chemicals.
So he was looking for a common thread, a unifying principle that connected all these seemingly different forms of electricity.
And he found it. Faraday demonstrated that regardless of the source, electricity consistently produced the same effects, whether it came from a voltaic pile, a Leyden jar, or even an electric fish. It was fundamentally the same force, just manifesting itself in different ways.
It's like he was revealing this underlying unity of nature, showing that beneath the surface diversity, there were these fundamental laws governing the behavior of the universe.
And this realization had profound implications. It meant that electricity wasn't some magical substance, but a fundamental force, just like gravity, a force that could be harnessed, controlled, and put to work.
And harness it he did. Faraday's next big breakthrough was in the field of electrochemistry. He went beyond simply observing the effects of electricity on chemical compounds. He meticulously quantified the process, laying down the laws of electrolysis.
This is where he really shines as a scientific pioneer. Faraday showed that the amount of substance decomposed during electrolysis was directly proportional to the quantity of electricity passed through it. Double the electricity, double the decomposition. It's a simple yet profound relationship that forms the basis of modern electrochemistry.
It's like he was creating this recipe book for chemical reactions, showing how electricity could be used as a precise tool to break down and build up matter.
And he didn't stop there. He went on to establish the concept of electrochemical equivalence, showing that different elements decompose in proportion to their chemical equivalents when subjected to the same amount of electricity. This was a crucial step in connecting the world of electricity with the world of atoms and molecules, paving the way for our modern understanding of the atomic nature of matter.
So he was essentially laying the groundwork for a whole new field of science, one that would revolutionize our understanding of materials, energy, and the very building blocks of the universe. It's incredible to think how much he achieved with the limited tools and knowledge available to him at the time.
It's a testament to his genius, his meticulousness, and his relentless pursuit of understanding. And we're still just scratching the surface of his contributions. There's so much more to explore in these volumes.
Well, in that case, let's take a break, and we'll dive back into the fascinating world of Michael Faraday in the next part of our deep dive.
One of the things that continually amazes me about Faraday is how he wrestled with these fundamental concepts that we take for granted today. Like, take the idea of electric current, for example. He actually questioned whether a positive current even existed.
Really? I mean, we're so used to thinking about electricity flowing from positive to negative. So what was Faraday getting at?
Well, he was deeply skeptical of oversimplifications. He was always looking for this deeper, more nuanced understanding. He argued that electricity wasn't a one-way street, but this dynamic interplay of forces. He often talked about, two equal and opposite forces, emphasizing that electricity was always about a balance, an interaction, a kind of push and pull between positive and negative.
It's like this, a dance between two partners. You can't have one without the other.
Exactly. It highlights this interconnectedness that Faraday saw everywhere in nature. He even compared the flow of electricity to the idea of two interlocking gears, always turning in tandem. It's a powerful image that captures the essence of his thinking. And remember, this was long before we had a clear understanding of electrons and the atomic structure of matter.
So he was essentially working in the dark, guided by his intuition and the results of these meticulously crafted experiments. It's even more impressive when you consider the impact his work had on shaping our modern understanding of electricity.
Absolutely. He was a pioneer in the truest sense of the word, blazing a trail through uncharted territory. And one of the key ideas that emerges from his work is this notion that electrical forces act through contiguous particles.
Okay, that one sounds a bit technical. Can you break that down for us?
Yep, sure. Think of it this way. Instead of imagining electricity as this mysterious force that leaps across empty space, Faraday envisioned it flowing through a chain of particles, each one influencing its neighbor. He often used this analogy of a line of people passing buckets of water to put out a fire. Each person represents a particle, and the water represents the electrical charge. So the charge is passed along, step by step, through a continuous chain.
Ah, so the electricity isn't jumping magically from point A to point B. It's moving through a medium, like a wave rippling through water.
That's a great way to visualize it. And this idea though revolutionary at the time, has become a cornerstone of our modern understanding of electricity. It helps explain how electric fields propagate, how currents flow through wires, and how charges interact with each other.
It's amazing how a simple analogy can illuminate such a profound concept. But Faraday didn't just rely on analogies. He backed up his ideas with these meticulous experiments.
Oh, absolutely. He wasn't satisfied with mere speculation. He wanted to see these forces in action, to measure them, to quantify them. And one of the ways he did this was by using spherical conductors, separated by different insulating materials. He was essentially building these tiny models to explore how electrical forces might act between atoms or molecules.
So he was using these spheres to simulate what might be happening at the microscopic level, invisible to the naked eye.
Exactly. He would charge one sphere and then measure the induced charge on the other sphere, carefully noting how the strength of the induction varied, depending on the material between the spheres. He was essentially mapping out this invisible landscape of electrical forces.
And what did he find?
He found that the strength of the induction wasn't simply a matter of distance, it also depended on the nature of the material in between. Some materials seemed to facilitate the transmission of electrical force, while others hindered it.
So the material itself was playing an active role, shaping the electric field.
Precisely.
Okay.
And he called this property specific inductive capacity, which we now call the dielectric constant. It's a measure of a material's ability to store electrical energy.
It's like each material has its own personality when it comes to electricity. Some are more conductive, others are more resistant.
That's a great way to think about it. And Faraday was fascinated by these differences. He meticulously measured the dielectric constants of a wide range of materials, from solids to liquids to gases. He even found that seemingly innocuous substances, like spermaceti, a waxy substance found in whales, had surprisingly high dielectric constants.
That's amazing. He was constantly unearthing these hidden properties, revealing unexpected behaviors in the most mundane of materials.
And he didn't just stop at static charges and induction. He was equally fascinated by disruptive discharges, those sudden bursts of energy that we see as sparks and brushes.
Oh, the sparks. Those always capture the imagination. It's like a miniature lightning bolt, a sudden release of pent-up energy.
And Faraday didn't just marvel at them, he meticulously dissected their behavior, revealing this complex interplay of forces at play. He found that the appearance of the spark varied depending on the type of gas it was formed in. He also noted that the shape and size of the conductors, as well as the distance between them, played a crucial role in determining whether a spark or a brush discharge would occur.
So he was essentially deciphering the language of sparks, understanding the conditions that led to their formation, and the factors that influence their behavior.
Exactly. And this knowledge wasn't just for the sake of curiosity, it had practical implications. Understanding how to control or prevent sparks is crucial in all sorts of electrical applications, from power grids to electronic devices.
Yeah, I can see how that would be important. Uncontrolled sparks can lead to fires, explosions,
Right.
or damage to sensitive equipment.
Precisely. And Faraday's work laid the groundwork for our modern understanding of electrical breakdown and the design of insulation systems.
It's amazing how his insights, gleaned from this meticulous observation and experimentation, continue to shape the technology we rely on every day.
And it all stems from his relentless curiosity, his willingness to delve into those nitty-gritty details, and his ability to connect those details to these broader principles. He saw connections everywhere, from the Earth's rotation to the spark from a static machine, unifying seemingly disparate phenomena under this common framework of electrical principles.
It's like he was building this grand tapestry of knowledge, weaving together threads from different branches of science, revealing this interconnectedness of the universe.
And he did it all with this incredible humility and a deep respect for the natural world. He recognized the limitations of his own understanding, always acknowledging the possibility of error and the need for further exploration.
His work is a testament to the power of scientific inquiry, the relentless pursuit of truth, and the enduring legacy of a truly remarkable mind.
Absolutely. And what's truly inspiring is that he wasn't driven by fame or fortune. He was driven by this pure love of knowledge, this desire to understand the world around him, and to share that understanding with others. His work continues to inspire scientists and engineers today, pushing the boundaries of knowledge and driving innovation.
And speaking of innovation, Faraday's discoveries didn't just sit on the shelves of libraries. They had this profound impact on the development of technology, leading to countless inventions that have transformed our world.
His insights into electromagnetism, induction, and electrolysis paved the way for everything from electric generators and motors to batteries, telecommunications, electroplating, and the production of aluminum. His fingerprints are all over the modern world.
It makes you wonder what he would think if he could see the world we live in today.
I imagine he would be both astonished by the technological advancements and humbled by the enduring power of these fundamental principles he helped uncover.
Well, we've covered a lot of ground, but there's still more to explore in the fascinating world of Michael Faraday.
Indeed, his work on specific inductive capacity, the influence of temperature and pressure on electrical phenomena, his investigations into the behavior of different gases under electrical discharge, each one is this treasure trove of insights.
So let's take a deep breath and dive back into Faraday's world in the next part of our deep dive, where we'll uncover even more fascinating experiments and groundbreaking discoveries. It's amazing to think, as we go through these volumes, that Faraday wasn't just interested in, listing out all these electrical phenomena. He was really driven by this deeper desire, this quest to understand the fundamental nature of electricity and its place in this grand scheme of the universe.
Yeah, like he was trying to decode the language of the cosmos,
Yeah.
using electricity as his Rosetta Stone. He saw these connections between electricity and other areas of science, like chemistry and magnetism, hinting at this deeper underlying unity in the forces of nature.
One of the things is where Faraday describes his vision of a unified field theory, this concept that wouldn't gain widespread attention until, decades later.
Oh, you're thinking of that passage where he writes, "I have long held an opinion almost amounting to conviction, in common, I believe, with many other lovers of natural knowledge, that the various forms under which the forces of matter are made manifest have one common origin, or, in other words, are so directly related and mutually dependent that they are convertible, as it were, one into another, and possess equivalence of power in their action."
It's really a remarkable statement, especially considering he wrote this in the 1830s, long before Einstein's theories of relativity and the development of quantum mechanics.
It's incredible.
It's mind-blowing to think that he was already grappling with these ideas, envisioning a universe where seemingly disparate forces, like gravity, electricity, and magnetism, were all interconnected, different expressions of a single fundamental force.
It speaks to his incredible intuition and his ability to see beyond the limitations of his time. He was a true visionary, paving the way for future generations of physicists to explore these deeper connections in the universe.
It makes you wonder how far science would have advanced if Faraday had access to the tools and technologies that we have today.
It's a tantalizing thought. But even with the limited resources available to him, Faraday's achievements were extraordinary. He made these groundbreaking discoveries, developed ingenious experimental techniques, and meticulously documented his findings with clarity and precision. His work wasn't just about generating knowledge, it was about sharing that knowledge, making it accessible to others, inspiring future generations of scientists and engineers.
I think that's what makes Faraday so inspiring. He wasn't driven by ego or the pursuit of fame. He was driven by this pure love of knowledge, a desire to unravel the mysteries of the universe, and to share those discoveries with the world.
His work is a testament to the power of curiosity, the importance of meticulous observation, and the enduring legacy of a truly remarkable mind. Faraday's insights continue to shape our understanding of the universe, driving innovation and inspiring us to push the boundaries of what's possible.
Well said. And on that note, I want to thank you for joining us on this electrifying journey through the mind of Michael Faraday. I hope you've come away with a deeper appreciation for the beauty and power of scientific exploration and the enduring legacy of a true pioneer.
It's been a pleasure.
Until next time, keep diving deep